Hello, everyone. Thanks for joining us today. My name is Tegan Clary. I'm the VP of Marketing at Unchained Labs. Thanks for joining us. I think this is going to be a great presentation of our bouncer instrument that's used specifically for helping people develop devices for delivering drug products and for other purposes. Today, we will be taking questions at the end of the seminar. So in the Zoom navigation bar, there's a little Q&A button. You just have to tap that, type your question, and send it in. Send in as many as you want. Please do it. We're not shy. And I know our presenter, Joe, will be happy to answer any of your questions. Without further ado, I'll actually introduce Joe Barco, our Senior Director of Marketing for our workflows and particle analysis business. Hey, Joe, how are you this morning?
Hi, Tegan. Good morning.
Joe's going to take you through the bouncer, how some of our customers are using it specifically for developing these types of devices. And Joe, I'll let you take it away.
Thanks, Tegan. So good morning, everyone. Thank you again for joining us. What I'm going to talk about today is a device called Bouncer, which is primarily used to quality control syringes. And so as I used to be a scientist, or I still am a scientist, at least by heart and by brain, but one of the things that I often have to do in marketing now is to look for imagery that kind of matches and correlates with a story that we're trying to tell. And as I'm looking for things to talk about Bouncer, I come across this picture. And so if you're a scientist, you know how important technique is, especially if you want to really aggravate yourself, go look for pipetting eye stock photos, and you see how bad someone's technique is. But it doesn't take much to look at this treasure of an image and kind of come up with what is wrong and everything that's wrong with it. So first, her hands are dirty. Second thing is that I can actually see her hands being dirty because she's not wearing gloves. The third thing is that it's pulling in air and bubbles and who knows what particulates, because of the fourth thing, which kind of looks like from this image that he's actually somehow being able to aspirate through the crimp cap. So I don't know what this drug is. I just know I don't want it anywhere near me. But like this kind of highlights the importance of technique to do something that we all kind of take for granted when we go to the doctor. And this story becomes more important and critical when you start to think about a trend that's important in managed care, which is to actually have syringes pre-filled with the drug. So some of this is meant to simplify work at hospitalization stages or in hospital visits, but a lot of it is really to drive chronic care management directly to the patient, where they're not having to go into the hospital or to a doctor's office every time they need a dose of their drug. So that there's good reasons behind this. Like if you're hospital visits, if you don't go to the hospital on chronic care, you're more likely to take medication on time. If everything's pre-filled in the syringe, you're likely to get the right dose. And then even whether it's someone doing it at home or a nurse or a nurse practitioner in the hospital, you have less points for failure because you don't have to do fewer steps and you're more likely to maintain sterility. So all of this is great and good reasons to have drugs or think about drugs in pre-filled syringes. But the challenge now is that upstream and puts more pressure on drug manufacturing and development, because now it's a device to consider and not just a protein or a drug in formulation. And so you have to control for a lot of things. One of those things being people's personal techniques, is you have to make your device, in this case your syringe, foolproof so that anyone can do it. And that could be a trained person, an untrained person, someone with unsteady hands, someone who has trouble, maybe vision problems and things like that, all have to be kind of accounted for, and you have to kind of work around that. The part of that is ensuring that the syringe is working properly. And so there's this concept called glide force, which is when you push the plunger, that the syringe plunger is going to move smoothly and evenly in the addition, and it's not going to jam and stop up. Because you want to have an even glide force, you need that syringe barrel to be lubricated, and that often it turns into means it's coated with silicone. That coating with silicone is now another variable in this process, because that could potentially come out in the solution and be injected. And so you can't have too much silicone, you can't have too little. You have to make sure it's uniformly distributed along the barrel so that it behaves consistently. The additional complexity here is that for pre-filled syringe drugs, you generally want to move towards higher protein concentrations. And that in and of itself and the reason for that is because you don't want to have someone injecting 10 mils into themselves. You want them injecting a mil or less. And so the drug concentration has to be higher to accommodate for that. but that adds its own other complexity in terms of drug stability in that formulation, because I now have that at a high concentration. So these are kind of the challenges that people are facing in terms of in quality control for QC syringes, especially with in mind towards prefilled syringes. So what does Bouncer do? Bouncer addresses a part of this problem, which is to look at the syringe coating. And so Bouncer has a technique that allows you to look at and measure the thickness of the syringe, siliconization in the syringe, and the distribution of that silicone throughout the barrel. And with that information, you can extrapolate the silicone mass within the device, as well as get a picture about how it's distributed. The techniques it uses are fairly straightforward. So if you look at, it uses a concept called interferometry, which is, you see this every day when you look at something and you can kind of see a color from it. So you shine a light on a surface, it hits that surface, some of the light is absorbed, some of it is reflected back. In this particular case, what we can do is use that information to look at how it's reflecting back off of glass, which has a certain refractive index, and then how it's reflecting back off silicone, which has a different refractive index. And so the transitions between air to glass, glass to silicone, and then silicone to air can all be measured and detected by Bouncer. And the differences in terms of how that intensity comes back is what will allow us to extrapolate the thickness of silicone within the syringe. There's two ways that this technology is used in Bouncer. One is that it uses just white light reflectometry. And so conceptually, both of these things do the same thing, which is I'm shining light on it, and I get a refractive index and an interference pattern back that I can extrapolate into a dimension. White light allows us to do a detection limit or a range of concentration of distribution measurements for silicone between 80 and 4,000 nanometers. And generally that ends up being a couple things. It ends up being glass syringes, plastic syringes, generally with a sprayed on silicone process, which usually is a thicker amount of silicone. The second piece of this is sometimes laser interferometry. And laser interferometry is just a different light source, but pretty much the same concept. And so what we can do with the laser interferometry is get down into a lower thickness level that we can detect and quantify. Generally, that ends up being glass syringes that have a a baked on silicone process. So between the two, you can get a pretty large dynamic range of silicone that would appear within the device. The way Bouncer works is, imagine a microscope stage or a microscope. You have a microscope stage that's modified to hold a barrel over the syringe, as you can see here. So we're going to shine a light on it. What we're going to do is move the stage in one axis, Y, which is along the length of the barrel, measure light and detect the interference coming back, march along, measure it again, and keep basically marching down the length of the syringe. Then once we run a full length down the syringe, we're going to rotate the syringe barrel automatically and then march back. And then I count, essentially to determine light reflecting back at that angle. And you can just repeat that process until you've gone around the syringe. And what you eventually get is a view like this, which is, you can see a heat map of the layer thickness or the silicone distribution down the length of the syringe barrel at that one particular point. As you rotate it, you get a three-dimensional view of that, which is going to show you the overall distribution within the syringe. Technique-wise, what it's going to do is it's going to do the fast measurement first, which is the white light reflectometry. And so the white light reflectometry is going to go through a first pass and get measurements. And if the measurement is above 80 nanometers, it's great. That's the measurement. It moves on, and we're going to go through the whole thing. If you get to the end and there's points where the detection limit is below 80 nanometers, what it's going to do then is go back with the laser interferometry, which takes a slightly longer time to do that measurement and capture the data for silicone thicknesses between 20 and 80 nanometers. So that's basically how it works. What I'll do is I'll talk about two case studies. And these are studies that our customers have presented or recently published on this, on how they use Bouncer in their laboratories. First is a paper from Roche in Basel, and so this is from 2018. This group is actually looking at, okay, this method. Let's look at this method. If we were to use this method to quantify and determine the coatings of syringes, how would we have to do that effectively to know that we're getting the right answer? And so basically, there's a method development process that goes along with this. And so there's a method development, and then they're going to compare it to another technique which is used for this, which is to do 3D laser scanning microscopy, or 3D LSM. And so they're going to compare that to another laboratory technique that would normally be used by them in this particular case. In this particular study, we're going to start with 3 syringes. So these have a known silicone distribution, so they're sprayed on silicone. Syringe 1 has a average, is basically a homogeneous thickness to the silicone coating. Syringe 2 has a thicker layer of silicone at the flange, the top of the syringe barrel, and then that decreases as you get towards the needle. And then syringe 3 has this blip in the middle that has a higher level of silicone present. So this is a 1 ml glass syringe. So there's a lot of parameters that they're looking at. And so first is how many times around the barrel do I have to go? How many increments of the barrel do I have to go to get a representative measurement of what's happening within the syringe? How many times along the syringe panel do I have to stop and measure? And then how far along the syringe barrel do I actually have to measure to get a representative picture? They went through and did all of these characterization and techniques for this. So this first picture is, kind of take this one by one here. Let's look at first this left syringe. And so what you could see is, if I'm looking at this, the data points are the number of radial measurements that were made around the barrel of the syringe, so 0 to 360. Starting with black, you can kind of see this triangle here, which is the 3 measurements they did within this syringe. As you increase, you can kind of see, you get a picture about what's happening at each of these points. As I go to 3, 4, 5, 6. And then I can see as I go to 7, 8, and 12 that I get this extended out, and I get a more clear picture about what's happening on the edges here. ALT is average layer thickness. You'll see that in the next few slides a few times. So in a uniform syringe, you're getting a picture about what's actually the distribution is, and their determination was that 12 times around the barrel was enough to get about 96 and above % of what the total area or total amount of silicone within the device was. Now you can see that if I go to syringe 2, which has a different non-uniform thickness, you can kind of see that if I stop at 3, that I don't really get a good picture about what's going on. But as I get out to 7, 8, and 12, I can see that I have a much broader, much higher thickness that I'm capturing because I'm interrogating more incrementally. So I get a better picture about what's happening at that higher thickness level because of that. And I see a similar process at syringe 3, which is, in this particular case, if I stopped at 7 or 8, I still would have missed this non-uniform distribution that I'm capturing pretty effectively when I go to 12 measurements across. They also looked at the number of points along the barrel, and they determined that they went to 100 points per line, and they determined 50 was sufficient enough for the purpose of their study. So 12 measurements around 50 down the length of the barrel. Now, the next part of this was to compare this with this 3D LSM instrument. And so they had certified thickness syringes with a known certified thickness. And so they compared that. They can see they have good agreement with the LSM. And these next 4 instruments are white light interferometry or laser interference, which is the bouncer measurements. And so you can see that you have agreement here between above 90% for the bouncer measurements as well. They looked at this, which is not presenting on operator-to-operator variability, but then they looked at the same syringes across all 3 techniques, and there's good agreement between the 3 techniques about what the actual measurement is going to be. And then finally, in part B, you can see that they actually compared LSM with a bouncer measurement. Now, What I haven't mentioned is the LSM, two things. LSM is a destructive technique, and so you have to break apart, or cut the syringe down the barrel to be able to effectively get the measurement, which means you get one shot at doing this effectively. When the solution or when the silicone layer is homogeneous, that's fine, right? So, and because any point along that syringe barrel is going to look like the other parts that you're not capturing. However, when you get to cases where it's non-homogeneous, you are going to miss data. And so they show that here, which is, in this case, we referenced that, 0 degrees is where all of these, where LSM and the bouncer make the measurement, and they're pretty consistent measurements. But the LSM would miss this non-uniform thickness in this area because it's not able to interrogate radially along the syringe. So finally, this is a summary of some of the conclusions from the paper. This table is basically showing that the key differences, the advantages of the LSM are two things. One is that you get actual images of the syringe barrel directly, where that's an indirect measurement for bouncer. Second is that it has a lower limit of detection, so I can measure down to 10 nanometers instead of 20 nanometers. I'll point out in this paper that they established that the optimal range for their syringe was 100 nanometers silicone thickness. So, the fact that you can get from 20 to 10 is probably not, again, fit for purpose. It's that extra sensitivity is not warranted in that particular experiment. In this case, though, what they're also looking at is, the amount of time it takes to make a measurement and all the other information you get from bouncer. And so getting the measurement from bouncer is about 4-fold faster than it is to get the same measurement from LSM. And you can get this other additional information on mapping the syringe radially and longitudinally. From a sample prep standpoint, because you can just take the syringe barrel or syringe and put it on to bouncer versus cutting it up, bouncer wins because of that as well. The key takeaways that they have is that the bouncer and the 3D laser scanning microscopy are both kind of perform with similar precision and accuracy. And if the method is uniform for coding, these both work essentially the same. There is a difference here, a distinction here, which is bouncer does the additional mapping. And they point out as part of their study that they saw large variations of batch to batch, which makes it important for them to test a high number of samples from each individual siliconization batch, which I'm going to editorialize a bit, means you need some way to quickly measure samples and do it in a way that anyone can kind of walk up and do it. So it doesn't need to be a trained operator working the microscope. It can just be a trained technician who can, feed samples into that device without creating a complicated process. Okay, so that's the first paper. The next paper is to look at formulation development in prefilled syringes. So this is a very recent paper. This is from August. This is from bioproduction group at Eli Lilly. And they're asking a fairly straightforward question, which is how do surfactants that would be present in the formulation, and how does the protein concentration impact the syringe functionality after it's been in long-term storage? And so this is a formulation stability study, which is a very common thing to be looking at biologics, but in this case, it's within a prefilled syringe. There's a previous paper cited here, which I'm not talking about today, which actually looks at a larger, broader formulation study. This kind of jumps a little bit ahead and is looking at optimization of the actual surfactants that would be used within that formulation. So from a study standpoint, there's 3 things to compare. There is the surfactant, and so they're looking at 2 different surfactants at the outset, which is polysorbate 80, and another one called polaxamer 188, or it will be P188 for this. They're looking at that in the barrel, in the formulation with and without protein, and they're looking at 2 different formulations, one protein at pH 5 and one protein at pH 5.5. So there are 2 different proteins within each formulation. So pH 5 has protein A, which is not the protein A, it's a protein labeled A, and then formulation B has another protein B at that pH. So they looked at surfactant, they're looking at the surfactant differences. They're looking at how does that impact changes, how do the changes occur if they have higher protein concentrations in those same solutions, which are at 50 and 100 milligrams per mil. And then finally, for reasons you'll see, that they expanded the study to look at other surfactants, P407 and maltoside. Their study conditions or stress conditions are fairly typical for biologics stability screening, which is to store samples at 0, 25, and 40 degrees C, and then to come back and measure or to measure, look for stability at T0 and then 1, 2, and 3 months. Now, the way they use this from a device standpoint is there's a couple different types of measurements that they do. First, they do Schlieren imaging of the syringe. So before they do anything else to it, they take it out of storage, and capture images of the syringe barrel. The next thing they do is they run a compression test, which is to confirm and determine the glide force necessary to eject the solution within the syringe. And then there's two things that happen. Their now empty syringe barrel goes to bouncer to measure the silicone thickness across the barrel, and their solution goes to particle analysis, which in this case are using MFI to see what particles are in the ejected solution. So I'm not going to cover all the data in this because there's a lot of permutations here. I encourage you to read the paper. It's very, very good. But from a summary standpoint, let's focus on one thing, which is this formulation A. And let's start with the left-hand side of this graph, which is the P188. So if I'm looking at P188 at any of these time points, at any temperature stored, and at any concentration, I have a pretty consistent glide force. Those of you who are not using this glide force measurement before, just to be clear, low glide force is better. High glide force is bad. It means you need more force to push the syringe, which is more likely to create a device jam. So on P188, there's no significant variation over time or regardless of protein concentration. This is not the same story for polysorbate 80, which if I look at lower protein concentrations at 25 mg per mil, I can start to see at the high stress temperature and time points that I see a higher glide force occurring. As the protein concentration increases, I start to see that coming up at a intermediate stress condition. And at high concentrations of protein, and I see pretty significant glide force differences of about 3 to 5-fold if I compare that to the low temperature storage. So in this case, the P188 is independent of, the performance is independent of drug concentration and independent of the stress condition, whereas polysorbate 80, higher glide force as protein concentration increased and the stress condition, which correlates to the longer term storage, increased as well. So let's go back and look at the images for these syringes. You can see if you look at the images of before the syringe was ejected, you can see these droplets showing up of silicone oil that shows up in the Schlieren imaging on the polysorbate 88, the P188. If you look at the polysorbate 80 syringes, there's no droplets. And so that somehow that syringe, that is not maintaining that syringe, that silicone coating. Let's look at the next step, which is to look at this on bouncer. And so you can see this heat map of these protein formulations. So 50 and 100 mg per mil, polysorbate 188. You have this green and blue area, which correlates to a higher thickness for silicone. Where in polysorbate 80, this is pretty much back down into these lower levels, so into the purple range. So at the actual measurements, polysorbate or P188 actually has a silicone thickness greater than 50 nanometers, where polysorbate 80 is generally under 20 nanometers of silicone left. Now, it's pretty obvious if it's not on the syringe barrel, it must be in the actual solution. And so that's where the MFI measurements come in. And they can kind of see that in this case, if I look at just formulation A, that P188, I have fairly low amounts of particle counts. This 5 micron is what's determined later to be silicone droplets. Where polysorbate 80, I see a pretty high increase in particles, especially as I increase protein concentration. The same thing occurs with formulation B, which is protein B, although to a smaller extent than it does with formulation A. So what they wanted to do is look at formulation A in more detail and understand why you see this stark difference between these two different surfactant types with respect to syringe performance. And so what they did is they added in these two additional surfactants, so P407, poloxamer 407, and maltoside. Neither one of these are used in biologics formulations, but these are good kind of intermediate surfactants to kind of piece this information out. So they started with just formulation A and one concentration, this 25 mg per mil, and then they looked at the glide force again. And so again, P188, low across all the stress conditions and all the time points. P407, it starts to come up, glide force starts to increase at the higher stress conditions. Polysorbate 80 is worse than that, and multicide is even worse than that, where you have 5 to 6 fold increases in glide force at the high stress condition. Okay, so what's causing, what does this correlate to? So they looked at critical myocyl concentration. There's not a clear correlation here, but what they looked at is this parameter called hydrophilic lipophilic balance, or HLB. And that's a parameter that basically gives an idea about solubility of surfactants in solution. So the higher the HLB, the lower it is, the less soluble it is in water. And so, I think I have that right. Where the lower HLB in this case is more soluble in water, or less soluble in oil, and so you're more likely to keep it within the syringe. So in this, when they started to look at the particle analysis for this, they captured that there is this correlation as well with the particle type and particle size. Multicide, even though it's showing low, is that it's actually producing enough silicone droplets that they're large and visible, and so it's not being detected by the instrument. But you can kind of see the same parameters and behavior in the bouncer data, which is you have higher silicone thickness of P188 of greater than 50 nanometers, and everything else is below 20 nanometers. So what this does is it gives some correlation, some idea about all these parameters that can be looked at to understand biophysically what's happening within the syringe and long-term stability. So what this kind of comes down to is that all of these parameters are interacting together. And so it's hard to make for formulation studies, you're not going to want to just pick a surfactant and be done. It's going to be very much a factor of what else is in that formulation and the concentration of drug. And so all of these interactions need to be studied together and not separately. And so the syringe function is going to correlate with the silicone distribution, which is good because you have multiple ways to get to the silicone distribution determinations. Where bouncer giving you the thickness appearance across the actual syringe barrel. I hope what I've shown you today is some idea about how bouncer can be used to QC devices. You can use it to QC the actual silicone coating process, but what this also tells you and talks about is how you could use bouncer to look at storage studies and to look at the parameters of the syringe barrel in long-term stability studies. So you can use it for QC as well as method development and characterization for formulation screening for this much more complicated project of pre-filled syringes. I hope I've given you some ideas about how you might be able to use bouncer. If there's other ideas that you come up with that aren't quite in line with this, please reach out to us at info@unchainedlabs.com and we'll help you out. And we now can also take questions. If you have questions specific to the talk, I'm happy to answer them. So welcome back, Tegan, to moderate the Q&A, and thank you everyone for your time and attention today.
Hey, Joe, thanks a lot for just walking through some of those workflows and how people are using bouncer in that workflow. I think to provide some insight that other things cannot. So I think you did a good job explaining that. We do have some questions. Let's tackle those right now. Okay. The first one in here is there a limit to the syringe size that can be used in the bouncer?
Yeah, so there's a little bit of a practical limit because of what, from the picture, you can probably see like kind of what can fit on the stage, but like that ends up, and what can fit under the objective, but it's still pretty broad. So pretty much any normal syringe type, like that's up to about 90 millimeters long, can be used in the syringe or on the stage. And there's two different stage types that can be used for different syringe diameters.
Okay, great. Does it have to be a syringe, or are there other types of devices that people can use on the system?
No, it actually just needs to be circular. So you could use vials, and I think we do have one customer who's looking at coatings within vials. So syringes is up to 22 nanometer diameter. For something like a vial, which maybe is 48 millimeter diameter, you can use that as well.
Okay, great.
Up to 48 millimeters.
Another question here, what type of sample prep do people need to do before they put the syringe on the instrument? Is there something they need to do?
They need to empty the syringe. So that's and remove the barrel. So you got to make sure that there's a path of light that can go through. And so if you're storing a solution, if you're storing a drug in the syringe, you have to expel the solution first, and then you want to dry that to ensure there's no droplets remaining. And you do that in a passive way, either a vacuum or a desiccator. So that's not going to disturb the silicone layer. You also want to have control samples. So if you're measuring silicone thickness, you want an uncoated syringe as a positive control. And depending on the complexity of your study, having a syringe that has no drug in it but has been stored or is also good as a control.
Okay. Does the bouncer have an autofocus function? How does it focus in on things?
It does. So someone can set the bouncer set focus at the outside of the experiment. You can autofocus on or off, but it does. The first paper I referenced for Roche, they actually did look at that comparison of how well the autofocus works, and they ended up not presenting the data because they're like, it's just as good as someone doing this manually. So, yeah.
Okay. Another one here, just how long does a measurement typically take on the bouncer? I think you mentioned it's 4 times faster than something else, but how long does it take?
Yeah, so it depends a little bit on how long the syringe is and how many radial points you're going to take. And so, and also whether it's going to it only needs to get the measurement from white light interferometry. So it's kind of baseline I use is like if I go 6 lines around the syringe, about 45 millimeters long. That's about 5 minutes if I do the white light measurement. So about 5 minutes for a typical sprayed on siliconization. If you need to go to laser interferometry, it may be like about 3 to 4 times that, so like 20 minutes total.
Okay, great. Joe, a question here, can you get a mass for total silicone in the syringe from the system?
Yeah, it does that. So because I have all my dimensions, and so it calculates it because I know the volume of the syringe, I know the diameter of it, I know the length of it, I have an average thickness that I get out of the measurement, and if I have a specific gravity of the silicone that I'm using, I should be able to calculate a total mass. So bouncer, one thing in terms of people have compared that to a full extraction of silicone, which they didn't have to do in other cases. You do have a bouncer doesn't measure the top of the flange, and it doesn't can't measure that very end of the glass where it's concentrated at the surface. So you kind of have a systematic, error for a syringe because it can't get quite those last 2, pieces of where the glass is thicker. But other than that, and even taking that into account, you can still get a measurement for the total silicone mass.
Okay. And you'd mentioned emptying the syringe. There's a question here. Does that impact the accuracy of the measurement, the emptying of the syringe?
Yeah, I think is also the Roche paper, but I'm not 100% sure they looked at that as well, which is the process of ejecting the syringe, the material through the syringe barrel itself does not disturb the silicone layer, nor does drying it out. And you can even rinse it with another solution if you're and then dry it out, and it's still intact and the same, unaffected.
Got it. Okay. This is the last one for you, Joe. The question here is what's the meaning of layer thickness for silicone on surface as droplets? Does this concept of, I think the question is, the drop versus layer affect the syringe performance? Do we have any information on that?
The drops of silicone?
Yeah, I think it's just the meaning of layer thickness with either a layer or droplets. Do we distinguish those? Is there some difference between them?
So if we wouldn't be able to measure droplets. So the way it's like a 45 micron average point field of view. And so like if there's droplets, I'm more likely to miss if they're smaller or around that. So it's not a full mapping. It's over points. I think I'm maybe not getting the question, because I think generally in this you're going to have a uniform layer. So maybe there's some other application that someone's thinking about an uneven coating or a non-homogeneous coating.
Sure. Yeah. No, fair enough. Well, it's a good opportunity for whoever asked that question. Reach out to us. We'd be happy to talk to you about that in more detail. And Joe, thanks for a great presentation. For any of you that do want to talk to us more about Bouncer, Joe mentioned, you can go to our website and put in a request to meet with us or talk with us. We are really good at doing virtual demos and actually showing people our products and what they can do for people virtually over Zoom. We're happy to do that with any of you, and please reach out and don't be shy. So again, thanks Joe for a good presentation and for answering all those questions, and thank you to all of you who joined us today. I hope you have a great rest of your day.
Thank you.